Preparing for organic chemistry exams comes down to mastering two core areas: naming conventions and reaction mechanisms. The foundation of the IUPAC system relies on identifying the longest continuous carbon chain and assigning the lowest possible numbers to any substituents. With two or more functional groups, apply a strict priority hierarchy to determine the principal functional group. Scanning down the reactivity order, carboxylic acid sits at the absolute top. Moving down, we see acid derivatives, carbonyls, and alcohols, with halogens at the very bottom. Correctly identifying that highest priority group is your mandatory first step, because it dictates the primary suffix and structural name of the entire molecule. Chemical reactions are driven by attacking reagents. Nucleophiles are electron-rich species, seeking positive sites, while electrophiles are electron-deficient and seek out electrons. To understand how these reagents interact, we evaluate four electronic displacement effects. First is the inductive effect, a permanent dipole created by differences in electronegativity. In a carbon-chlorine bond, the more electronegative chlorine pulls electron density toward itself. This dispersal of charge stabilizes the resulting conjugate base, which directly increases the molecule's acidic strength. The electromeric effect, by contrast, is a temporary complete transfer of pi electrons. This shift only occurs on demand, when an attacking reagent is actively present to force the polarization. Next is the resonance effect. Here, electrons are delocalized across multiple contributing structures, reducing overall energy and increasing the stability of the molecule. Finally, steric effects describe the physical crowding caused by bulky groups. Large substituents surround the central atom and restrict access to the lone pair, which prevents incoming protons from binding and weakens the molecule's basicity. By analyzing these four invisible electronic forces, you can accurately predict how a specific molecule will respond to an incoming reagent. Nucleophilic substitution is the most highly tested reaction mechanism. It splits into two distinct pathways, determined entirely by the physical structure of the carbon substrate. This top graph illustrates the SN1 unimolecular pathway, a two-step process favored by bulky tertiary halides. First, the leaving group departs to form a planar carbocation. This geometry allows the nucleophile to attack from either side, generating a racemic mixture. Contrast this with the bottom graph for the SN2 pathway, a single-step process favored by uncrowded primary halides. The nucleophile must attack from the back, creating an unstable transition state that forces the remaining bonds to flip, a Walden inversion. Ultimately, whether a reaction proceeds via SN1 or SN2 is a direct competition between intermediate carbocation stability and the degree of steric hindrance. First, locate the carboxylic acid to establish your principal functional group. Then classify your substrate, tertiary for SN1, primary for SN2. This accurately predicts reactivity.